Welcome. This is the third in our series of lectures on demand-side management. I'm Clark Gellings. I'm a fellow with the Electric Power Research Institute. Of course, this series is being produced by the University of Minnesota. The current opportunities that I want to talk about here are for demand response and how it might be implemented. I'm going to use as an example here opportunities in the PJM markets. And PJM, the Pennsylvania, formerly called Pennsylvania, Jersey, Maryland interconnection, is the largest RTO in the United States, and I think the second largest in the world, second only to one of those in China. And they operate wholesale markets around a number of items or products, they call it, which include forward capacity sales, day-ahead energy sales, real-time spot energy sales, energy and capacity payment for emergencies, day-ahead scheduling reserves, synchronized reserves, and regulation. Demand-side management fits in one way or another into all of these. What does all this alphabet soup mean if you're not familiar with it? Essentially means that we have here a wholesale market operator as well as a transmission and generation system dispatcher who operates so as to optimize the wholesale price of electricity for the utilities that are part of the PJM system, which are a large part of the utilities in Pennsylvania, New Jersey, Maryland, and a bit to the west as well. The wholesale price in a entity like PJM changes every hour. Here's a plot of wholesale hourly prices. The acronym LMP means locational marginal pricing. They actually calculate prices down to a very specific area that would be essentially a distribution or transmission substation and the bus on that substation. The retail rate, for example, in many of the PJM customer areas that's charged might be something in the order of, I don't know, $70 per megawatt hour or 7 cents a kilowatt hour, and that's the retail rate, whereas the actual price of wholesale energy could at the same time be as high as over $300 per megawatt hour. And it's that difference that you need to draw your attention to in looking at this difference between the the retail rate, that rate that's being charged, and what is the wholesale rate. And this acknowledges the fact that at certain times there is enormously high prices of generation in response to what probably is a near peak load at that time. And so the objective of demand response in this case is to try to reduce the wholesale price of electricity at those critical peak times. And the question that comes from this is, will an end-use customer reduce consumption when wholesale prices are high, or when PJM, the RTO in this case, regional transmission operator, indicates emergency procedures? What they have done in the last few years, they've gone out into the marketplace and they've asked for entities to come forward with bids as to how they're going to provide capacity for the growing demand for electricity in that region. And three different resources are allowed to bid. One is generation, and these are entities, including utilities, who might come forward and say, I will build generation capacity for you, and that will help solve your problem in part of needing additional capacity. We've had, in this same offering, suggestions that demand response or demand resources, as they're titled here, might satisfy some of that. And in a more recent bid in 2012-2013, energy efficiency was included. If you see the enormous increase from 2011 and 12, where 16% of the bids were for demand resources, to 77%, a large fraction of the bids coming from demand resources and energy efficiency. I might suggest that this also speaks in part to our first in the lecture series here, of the fact that there's a basket of things, programs, and initiatives that are included in demand-side management that might well displace the need for traditional resources. Here's a perfect example of that. And it's not just in Pennsylvania, New Jersey, Maryland, but New England, in this case, showing the New England Independent System Operator, has also solicited for a variety of different kinds of capacity. And as you can see from the labels of energy efficiency, demand response, and the like, that there is an enormous amount of capacity that are being bid into the, in this case, called forward capacity auction, and would be available, therefore, to supply the New England area in place of what traditionally would have been generation. Now, there is some limitation to this, as highlighted by this plot from PJM from a August 2nd, 2006 occurrence. They had a projected peak of 9,443 megawatts, and they projected what the peak would have been with and without demand response in this case. And they found that they're getting a kind of a rebound effect in one sense, and they're having to deal with a new peak in another sense. In other words, it's so successful at reducing the peak that now we have to worry about the demand before we actually implement demand response and the peak after we implement demand response, because the effectiveness of demand response, in this case totaling about 7%, has a limit in terms of what and how long you can use it. If you're controlling air conditioner, you can't shut them off forever. That's pointless. If you're controlling an industrial process, you can only control them for so many hours. So here again, we're looking for technology to help us mitigate what might otherwise be a less effective demand response program. Of course, one of the things that we've been investigating quite seriously and have been used a bit in the industry are energy displays, where essentially I put in a device in a building, a number of manufacturers for this, that give me information about what's going on with my electrical use. Either tell me the demand or the time, or even do it as a cents per period of time, a rate of energy consumption, or do some diagnostics, more like an energy detective. And these energy displays also have an impact potentially on reducing demand for electricity. It turns out that this information in many places, is critical to end-use decisions. The habits, of course, of residential users particularly affect energy use enormously. And then feedback that we'd offer through these displays helps the customers understand the cause and effect between their actions and their bill ultimately. The behavior and its consequences therefore get kind of a direct link. So if you take a compilation of studies, some of them that have been done, there's potential savings of 4 to 15% in energy as a result of these devices being available. In one study in Hydro One in Hydro Quebec, there was a 6.5% average saving. And in another study, there's a 12% average saving at Salt River Project through the use of what are called 55,000 prepayment meters. Salt River Project serves an area surrounding Phoenix. Prepayment meters are meters where you have to prepay for your electricity. And by prepaying, you become extremely conscious about what the price of electricity is and how much you're consuming. So these devices could well be implemented as part of what we are calling the smart grid. That is this idea that we will overlay communications, control, and computational ability on the power system in a variety of ways so that we make better use of the assets overall. At the same time, have the ability to integrate customers more fully with the power system. Once we have some of the aspects of the smart grid installed, installing these devices will be really easy. The next step to this is to think about a program called dynamic energy management. So the idea of demand of a dynamic system is to take day-ahead hourly prices, such as being taken now, and actually use that information to feed into smart end-use devices that might be located at the customer premise. So I'm no longer just balancing supply and demand in the traditional way, but I'm also including what I consider to be changes in the demand I can make as a result of knowing what the prices might be tomorrow, and by the way, as a result potentially of knowing what local weather might be. And so this is kind of a next step in the evolution of dynamic systems. Historically, we have had some time of use rates where we've had rather low penetration and response use of those rates. And they're really not verifiable without having a two-way communication system and the more elaborate analytics that would go with it. And there's been, of course, as I've highlighted in the second lecture, a modest use of load control. And that's beginning to evolve now into automated demand response, where we make this system automatic overall. We tie the communications directly into the devices so that we allow the devices to make a decision for us based on parameters that we give it. Tomorrow we see this moving to much more standardized design with interoperable devices that can talk to one another. We want to make it simple and automated so that we provide for the development of what we call here in this slide a ubiquitous system, so that the system of tomorrow in the consumer's building and premise learns what the consumer's habits are, learns the characteristics of the device and appliances, and then enables what is essentially and truly a dynamic system. Now here's a diagram that kind of shows the basics of this with an oversimplified building. This building might well have advanced metering, smart end-use devices. It has some kind of portal or building energy management system. We call it a consumer portal here, sort of the gateway for communications and electricity into the home. And the building could be a very efficient building. It might also be connected to the internet. The idea of the portal could well be a device that allows for consumers to interact completely through communications with the electricity system, choosing suppliers, selecting tariffs, monitoring usage, responding to price signals, monitoring appliances and devices, remotely programming operations. We see some of this now with things that are on the market. Either turn your lights off, remotely, adjust your thermostat remotely. It might consolidate bills. Instead of you having, if you own 4 McDonald's in one city, instead of getting 4 bills, we can consolidate all those. We can detect whether you're out of power or not, and not wait for you to call us. We can monitor the power quality and take action to at least dispatch crews to take care of it. Security, both from an electrical perspective, but also perspective of security for the building. Data management of various kinds, and entertainment as well, although obviously there's a lot of players these days in the entertainment market. And so the system of tomorrow, a more holistic view, might have a lot more technology, photovoltaics, plug-in hybrids, distributed generation, storage, and meanwhile in the distribution system, we might have distribution operations with dynamic systems control and data management. And all of this, remember, a communication system overlays it. So here's an example of a dynamic system. There's a control interface with your thermostat. It receives day-ahead hourly prices for electricity for the next day. You've already set an upper and lower limit as to where you would allow the temperature in the building to drift. The thermostat learns the thermal integrity of the building and how it responds to changes. It learns your preferences, and it's keeping track of weather impacts. And so the dynamic response might look something like this. I know the prices today, later in the day. I know the temperature. I know what's going to happen with the weather. I'm going to pre-cool this building. I'm going to therefore clip the peak to some extent, and then I'm going to allow some recovery later in the day. And I do all this through a smart device that incorporates all of these systems I said and does it dynamically. So, a short quiz. 2 questions. First, energy display devices. Do they provide information to enable end-use decisions? Do they enable consumers to be more efficient? Or do they reduce the time between behavior and the consequences? Of course, they do all 3. And then secondly, dynamic energy management systems. Perhaps they'll enable devices to respond to price signals. They might connect customers to markets, or maybe they'll inhibit energy efficiency. And of course, you choose the first two. They might actually certainly enable devices to respond to price signals, and they could possibly connect customers directly to markets. Imagine customers, even smaller customers, being connected directly to wholesale markets. I hope you've enjoyed this lecture, and look forward, please, to the next one.